presenter is Samuel Grauer from Dr. Steinberg's group, and he's going to be speaking about incorporating a priori Lineshape data into Bayesian hyperspectral absorption tomography.
All right, thanks. Yeah, so I'm going to be talking to you guys about Bayesian technique for absorption tomography that we've been working in Professor Steinberg's group. I'm a postdoc with Professor Steinberg, and I also work with Askar Kaspakov and Leslie Hsiao, and so we're starting up Professor Steinberg's group over here, who's previously of the University of Toronto, and so I'll get started. A little bit by way of motivation, which probably isn't needed in a room like this, but I'll just say a few words on it anyways. We're interested in imaging turbulent quantities in spatially resolved manner, so 2D or 3D, to basically get a sense of fundamental phenomena, observe them to begin with, and maybe develop models of what's going on. More specifically, we'd like to model combustion processes, and we'd like to get measurement data of combustion processes, especially in conditions where optical access is limited, and use measurement data to validate CFD codes and obtain closures for models. And finally, the application that's most relevant to this presentation is spectroscopic denoising. And so the technique that I'm going to talk to you guys about is going to be specific for this form of tomography, but it's sort of generally applicable to spectroscopic denoising applications, where you might get a fringe with your laser, or maybe a thermal noise. And in cases like this, where you've got a very low amount of signal and you're looking to do denoising, the technique that I'm going to talk about will address itself to that. And so in all of these cases, linear hyperspectral absorption tomography is a technique that we can use to image gases for observing turbulence, validating combustion simulations, and I'll introduce this Lineshape prior that you can use for spectroscopic denoising. So, what am I talking about? First, imagine that you've got a gas of some sort. We're going to have optics around this gas phase process. And we're going to shine laser light through it, and you can imagine that each of these beams is like a single beam TDLAS procedure. And then we're going to have some sort of representation of the gas, finite representation, pixels, or maybe a finite element mesh or something like that. And we will use a model of the physical process of light absorption and the model of the gases, and then we're going to use that discrete representation, invert the model for a set of data, and come up with a sense of what the gas state is in. So let's go over the model. First, we have line of sight absorption. And it's somewhat similar to the presentation we saw last time, where you've got the Beer-Lambert law, except in this instance, we've got a spectral absorption coefficient inside the Beer-Lambert law, which is going to be related to properties of the gas molecule that you're imaging. And we're going to transform the measured intensity into an absorbance, and then we get a linear relationship between this value kappa, which is the spectral absorption coefficient, and the measurement data. And so we need a model of what kappa is. We're doing this for many different wavelengths. That absorbance is for one wavelength. And so that A is actually a summation. And so you're adding up the spectral lines for many different lines of a wavelength. Each line corresponds to a rotational vibrational mode of the gas, and the details of that aren't really important, but the point is that you add up all of those lines, and then you get a spectral absorption coefficient profile that characterizes the gas. And so we're going to try to incorporate some information about this spectrum to get better reconstructions in a little bit. But the next thing to do is talk about how we're going to represent the gas in the domain. So here I'm using a finite element mesh. Basically, we're going to be estimating those values kappa for any given wavelength at the nodes of this finite element mesh, and we're going to want to approximate a distribution of kappa using linear basis. So here you see 3 linear basis functions, and we had that absorbance measurement earlier. The integral that we have for the exact form of the Beer-Lambert law, we're going to approximate with a sum of integrals over the basis functions multiplied by the value of kappa at the nodes. So that's going to be a representation of the flow at one wave number. And you do this for each line of sight and for each node, and then you get a matrix system where A is going to describe the Beer-Lambert law applied to this vector K, which is distribution of kappa, and B is going to be your absorbance data at one wave number, And then all that tomography really is going to be some way of inverting this system. And so you've dealt with matrices before, you might have seen a mesh, and then that's effectively how tomography works. So now it's really that simple. That's basically what you're doing. You're just inverting a matrix system. So the problem with that, the reason why it's not quite that straightforward, here you see just a sample beam array with a very limited amount of data, which is typical in these kind of experiments, and a ground truth phantom from an LES. And you can see that if you have a coarse grid, you're not going to have enough resolution to pick out the features that you're interested in. But if you have a fine grid and all you have is this absorbance data, you're not going to be able to reconstruct the features either, because you're going to have many more many more unknown variables than equations. And so you're going to have an underdetermined system and an infinite set of solutions that could explain the measurement data. So somehow we need to add information into this flow, or into this, about the flow into this equation in order to actually get a reasonable estimate out of the measurement data. So we use that, we use Bayes' equation to accomplish this. So we conceive of the measurement data and the model as random variables, and we characterize our knowledge about these in terms of probability density functions, PDFs. And so I'll just walk you through how this equation works in a brief way. So first we've got a likelihood function, and that says, okay, you might have a model of your flow that says what the measurement should be for a given state of kappa, but perhaps there are model errors, discretization errors in your flow. That finite representation of kappa isn't exactly the smooth kappa with high frequency features that you'll get in reality. And you'll also have noise from your laser, like I said, fringe noise or thermal noise in your system. And so even if you say that the distribution of kappa that you have should give you this measurement, there's going to be some spread on that, some uncertainty. And so we write out an equation that says what that uncertainty might look like. And again, this I can go into detail on later. But we're going to characterize the noise in the system using this Cholesky factor of the covariance matrix, this L matrix, which is going to tell us how noise for one absorbance is related to noise at other absorbances. And that's going to describe this function. And we're going to combine the maximum likelihood estimate with a prior PDF. And so this is sort of where the magic happens, so to speak. The prior PDF is how we impute our assumptions about the flow to regularize it and to avoid this ill-posedness. So we might assume that our flow is spatially smooth, or we might assume that we have a very thin reacting zone, and you might have smoothness within the reacting zone, but sharp discontinuities on either side. Or you might have more advanced knowledge about the variance in different regions of the domain. And in all of those cases, you're going to build those pieces of information into this matrix L. And so Bayes' equation tells us how we relate those functions together. And then we're going to get a posterior distribution. And the posterior distribution tells us, okay, subject to the measurement data you saw, and subject to the assumptions that you've built into your prior, what is the likelihood of any given value of x, or a kappa? And so what we want to do is find the most likely value of kappa subject to all of this information that we're putting in the equation, and that's going to be our reconstruction. And based on the equations I've showed you so far, again, the details aren't important, the qualitative sense of what I'm describing is important, but you can see that you get a nice linear expression for the maximum a posteriori estimate, which is going to be our reconstruction. But I'll give you guys a sense of what all of these terms mean now. So your measurement covariance, that LB matrix, is going to mostly depend on the discretization error. So the fact that you're representing a smooth field with some high frequency components with this linear interpolation is going to introduce an error, and we can approximate what sort of form the discretization error is going to have and the covariance of discretization error for the different absorbances by using progressively finer meshes and a large eddy simulation. That gives you a pretty robust estimate. And the other main form of this basic Bayesian algorithm is the spatial covariance. And so what I'm going to do for today's talk is introduce a really simple prior that has very few parameters and is robust and is physically motivated. So it's just an exponential autocorrelation. So we assume that fluctuations in the domain are going to correlate to other fluctuations in the domain, except with a strength that decays exponentially from the node. And so it's got two parameters, and you can fit these in a robust way without tuning your parameters very much. And so when you build this information into your reconstruction, you can see that even in the coarse case, if you use this prior, you're getting better senses of the peak value of that flow, and you're reconstructing the structure better. But also when you move over to the high resolution mesh, even though we only have 32 measurements here and it's fitting something like 500 variables, it's getting a pretty robust idea of where the peak is, the shape of the peak, and especially in regions where you've got multiple beams intersecting, you're able to resolve the features that you care about. But so that was for one wave number. And now what people do is they want to estimate thermodynamic quantities. You don't really care about kappa necessarily. And so you want to know the temperature, the volume fraction, the pressure. And the way that people have traditionally done this is they'll take all of those measurement models and they'll build it into one measurement model. And they'll say, okay, I'm going to estimate all of those thermodynamic quantities at each node, and I'll have a big nonlinear function that gives me one residual, and then I'm going to get my measurements and I'm going to try to minimize it and find the distribution that explains the data. And you can do it, but it's just an incredibly difficult problem to solve and has a super high dimension, and because it's nonlinear, you have to use sampling techniques to solve it. And so if you can avoid this approach, that would be advantageous. And so what we do is something called linear hyperspectral absorption tomography. And it begins by saying, let's just do the straight up Beer-Lambert law type reconstruction for each measurement wave number. So we're going to reconstruct, and then we get this block diagonal system. So we do those reconstructions wave number by wave number and get the spatial distribution of kappa at kappa 1, kappa 2 for all of the absorbances that we measure. And then we go through the domain, now that we have this full hyperspectral information, and we infer the quantities of interest on a local basis. So you can see that if you take those kappa vectors that we reconstructed, and you look at all of the vectors at one node, you're going to get the local spectra, and you can use that to determine temperature and pressure and mole fraction locally, and that's going to be an overdetermined regression. So that's how you're dealing with this. That's where you basically get your free lunch of reducing the dimensionality of the problem. So then the question is, what sort of spectral covariance will we introduce? Because if the prior that you would get for just assuming nothing about the relationship between these reconstructions is a block diagonal form of the spatial prior that you introduce initially. But we should know something about how the kappa at one wavelength will correlate to the kappa at another wavelength in another region of the domain, because the thermodynamic quantities are related and the absorption coefficient spectra come from those thermodynamic quantities. So we introduced a spectral prior, and we wanted to use minimal assumptions in building the prior so that it's not contingent on knowing a ton about the process. We want to know a little bit about the species that we're looking at, or multiple species that we're looking at. So the first thing we do is we assume that the covariance of each line is independent from the covariance of each other line. And the reason for doing that is the nonlinear relationship with temperature. So we calculate the expected value and get the covariance of a line for different parameters that you might see in the domain. And you just calculate the line for a large range of parameters that's going to more than encompass the conditions you'll see. Large range of temperatures, pressures, volume fractions, other participating species that affect the line shape. And then we get this covariance for the one line. We add up covariances for all of the lines that are going to be present for that species. And then we combine the spectral prior with the spatial prior by just taking the Kronecker product. So that says that we expect the spectral characteristics to be uniform throughout the domain, which is obviously not true, but the idea is to just add a little bit of information, knowing stuff that we definitely know about the gas, to improve the reconstruction. And so hopefully this approach is sufficient. So if you take a look at what this prior actually looks like, here you can see how variance at one wave number is corresponded with variance at another wave number, and this is for water. And I show the conditions that this was calculated for in the bottom there. But so you can see that if you've got strong lines, those lines are going to give you information about what's happening for the entire spectrum. So you can see you've got these big peaks that are going to influence the entire spectrum. And the idea is that if you have something like an increase in mole fraction, that's going to affect the entire spectrum in a uniform way. And so you can get information about what's happening at your minor lines from the major lines and hopefully reduce the effective noise. So to just test this quickly, we came up with a very small simulation of a turbulent water jet. Jet was about 1,000 Kelvin, and then we took measurements at a plane using a very high resolution mesh, and took a large number of measurements so we could get average reconstruction statistics and so on. And then we took absorbance data for this very limited data beam array, so again, only 32 beams, and we added a lot of noise, like way more noise than we would realistically expect to see in a TDLAS experiment. So we took 5% of the peak absorbance ratio that we observed in the entire experiment, added that was the standard deviation of our noise, and added that to all of the beams, regardless of whether they were seeing such high absorbances. And then we did reconstructions on the coarse mesh, and the reason was just for computational efficiency. So using this on finer meshes is how we're going to scale this up. And then I'll just quickly walk through the results here. So here you see the exact spectra to hot node and the exact spectra to cold node. And when you do your spectrally resolved absorption, when you do your linear approach without any spectral covariance information, you can see that in areas where you get a lot of beam coverage and have a lot of gas, you can already reconstruct the spectrum quite well. In areas where you don't have as much gas, you're quite noise affected, again, because we added so much noise to the data. But when you introduce the Lineshape prior, you get really, really good spectral information in areas where you have a hot node. And this is showing a place where the average estimates were quite good to begin with, so it's a favorable demonstration. But the cold node is an instance where you have not very much information about the gas, because you have limited coverage by the beams. And you can see that while the spectral prior was somewhat flexible, you do get correlated noise in your Lineshape. And when you go through and reconstruct, again, it's the coarse mesh, so you're not getting really nice features of the flow field. But you can see that you're reconstructing the peak mole fraction and temperature quite well and resolving some of the features that would be of interest. So to very quickly conclude, linear hyperspectral absorption tomography is a nice way to get images in areas where you have confined optical access and can only get a few beams in there instead of a camera. Lineshape priors can help you obtain more accurate spectral information based on characteristics that you know about the target species in the flow field. And there are alternative applications of this prior, such as spectrally resolved Raman and inferring absorbance data, and we hope to use this technique in those cases as well. So I have a couple acknowledgments there. Thanks for your time, and take any questions.
So how sensitive is the reconstruction to the approximations you make to form the prior?
So to the, it's not very sensitive, so this wasn't the first question, but the first thing would be it's not very sensitive to your likelihood function. It is quite sensitive to the prior, depending on how many beams you have. If you have a really dense beam array, then you're not super contingent on the prior. If you don't have a very dense beam array, you are somewhat contingent. But you can also do posterior uncertainty quantification. And so the idea would be that if you are not very confident in your prior, if you don't know the length scales, first of all, you can use this technique to infer length scales, but if you, like of an exponential decay. But if you don't have confidence in those, you widen your prior a little bit, and you'll just get wider confidence intervals in the back. So you are contingent on whatever information you add into it, and you could see the result where I had that very spotty reconstruction with no prior, and then the nice reconstruction with a prior. It's very dependent on the information you're adding in. But once you add in that basic idea of a correlation length scale, you begin to get pretty accurate reconstructions.
You mentioned that with more beams it's more accurate. Could you do something like almost like a continuous laser sheet?
Yeah, actually, that is one thing that Adam and I are working on at the moment with the spectral, is to possibly use a laser sheet in a certain application of this, and that's the best way to do it. So if you have a lot of measurement information, that's the ideal. It's just that in most of the cases where people are applying this, like in cylinder stuff, you're really just drilling a couple holes in and getting a few beams. So, but yeah, ideally the case you'd want to use a laser sheet basically. And like a line scan camera or something. Yep.
I might have missed this, but how do you, what physical parameters go into defining your prior?
The spatial prior or the spectral prior?
Both of them.
So the spatial prior really depends on what kind of prior. So for instance, you might have a total variation prior, which was the thin reacting zone thing that I said. And there it's basically a diffusion length scale of like how sharp you expect the boundaries to be. But in this case, it's the length scale of that exponential decay. And you would also estimate the variance throughout the domain. But the idea is to try to pick really simple priors where you're not going to do a lot of tuning to get the parameters that you'll use in reconstruction. And then in the spectral prior, you just need the range of thermodynamic quantities that you might see in your domain. So like minimum volume fraction, maximum volume fraction of the participating species, min-max temperature, pressure, and then maybe a few other things if you're dealing with a really advanced application where you'll have like line mixing or something.
Any other questions?
Yeah, so I'm going to keep asking this question if the speakers don't bring it up. Was there any challenges in this, when you were working on this problem, where you felt like you hit a wall? And
yeah.
How did you approach that?
Well, so it doesn't scale very well with the size of the domain. And so that's why I was showing reconstructions for a very coarse domain. And besides just throwing a lot of computational power at it, we haven't figured out a lot of tricks yet. But that's basically the current state of research on this, is trying to figure out how we can scale it up. Yeah.
And while you were developing the current state, was it like smooth sailing the whole time, or were there a couple of points where you thought, okay, maybe this is not working?
Yeah, I guess just getting to, like, there are a lot of small numerical tricks to get the inverse Cholesky factor of the covariance matrix. So things like maybe taking the eigen decomposition of it and chopping off the last couple nodes and stuff like that. And just if you just plugged in those equations to MATLAB, it would be very hard. There are a lot of little tricks along the way. And yeah, like basically it was a constant process of me phoning up the postdoc at my old lab, who's a mathematician, and being like, how do you invert these things? Why isn't this working? So, and then we had to come up with, there was a relationship on one slide that I didn't highlight where you can relate the Cholesky factor of the Kronecker product to the matrices that you were taking, the original covariance matrices that you were taking the Kronecker product of. And so without that expression, you can't really do it. So if you have to do the full Kronecker product of the covariance matrix and then take the Cholesky factor, that's not going to work. But you can take the Cholesky, just for numerical reasons, but you can take the Cholesky factor of the individual components and then take the Kronecker product of those L matrices, and then you can get the prior that you need, but it took us a while to realize that. So, yeah. So there were definitely, it was not smooth sailing. It was research, so.
Okay, let's thank our speaker.
Thank you.